What if everything we thought we knew about black holes was about to be turned on its head? Imagine this. A vast expanse of space where the pull of gravity is so strong that not even light can escape its grip. We're talking about black holes, these mysterious cosmic entities that have intrigued scientists and laypeople alike for decades. But what if we told you that the very concept of black holes and their singularities, those points where matter is said to be infinitely dense, might be up for debate? Yes, you heard it right. Black holes were first conceived in the early 20th century as a direct consequence of Albert Einstein's theory of general relativity. The theory suggested that when a massive star dies, it collapses under its own gravity to a single point in space-time, creating what we now call a singularity. Fast forward to 1963, and a physicist from New Zealand named Roy Kerr expanded on this concept. Kerr proposed a solution to Einstein's equations that described a rotating black hole, a more realistic scenario for the spinning stars in our universe. This was a groundbreaking discovery, and Kerr's solution remains a cornerstone of black hole research to this day. Then, in 2020, another physicist named Roger Penrose was awarded the Nobel Prize in Physics. Penrose's work demonstrated that black holes were not just theoretical constructs, but real astrophysical entities. His research showed that singularities, these controversial points of infinite density, are a necessary outcome of black hole formation. But here's where things get interesting. The very man who pioneered our understanding of rotating black holes, Roy Kerr, is now questioning the existence of these singularities. After more than 60 years since his groundbreaking work, Kerr has proposed a new theory that challenges our understanding of these celestial enigmas. But now, Roy Kerr himself is challenging the very concept of singularities in black holes. Roy Kerr, the physicist who discovered the space-time solution for rotating black holes, has recently presented a compelling argument against the existence of singularities. Let's delve a little deeper into Kerr's recent paper and his main arguments against singularities. The concept of a singularity, the central point in a black hole where matter is believed to be infinitely dense, has long been a key feature of our understanding of black holes. It's the point of no return, where the laws of physics as we know them break down. Now, Roy Kerr, who originally found the solution for rotating black holes in 1963, is challenging this very concept. In his new paper, Kerr uses a powerful mathematical argument to suggest that singularities should not physically exist. This is a radical departure from traditional black hole theories, which posit that singularities are an inevitable result of the immense gravitational pull within a black hole. Kerr suggests that instead of a singularity, there might be a central region inside the black hole where matter gets drawn towards but never actually reaches. This is a difficult concept to grasp, as it goes against the grain of what we've believed about black holes for decades. It's like suggesting that an apple falling from a tree never actually hits the ground, but instead gets forever closer without making contact. This argument is not without its critics. Many physicists still hold to the belief that singularities are a fundamental part of black hole structure. They point to numerous observations of luminous objects in orbit around black holes and direct images of event horizons as evidence. But what if Kerr is right? What if singularities don't exist? The implications are significant. It would mean a fundamental shift in our understanding of black holes and the laws of physics. It would be a testament to the fact that even in the face of seemingly concrete scientific consensus, there is always room for new ideas and challenges to the status quo. If Kerr is correct, it would mean a significant shift in our understanding of black holes. But what does this mean for the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull? Well, let's delve into that. The event horizon is a sort of point of no return around a black hole. Once you cross this threshold, you're committed to a one-way trip into the black hole, never to return. As far as we understand, this is a region where the gravitational pull is so intense that not even light, the fastest thing in the universe, can escape it. Now let's consider Kerr's arguments. He theorizes that singularities, the heart of black holes, might not exist at all. This is a radical departure from the conventional wisdom about black holes, which suggests that all matter within a black hole is drawn inexorably towards a singularity. This singularity is a point of infinite density, a point where our understanding of physics as we know it breaks down. So, if Kerr is correct and singularities don't exist, what could this mean for the event horizon? Well, it could potentially change our understanding of black holes entirely. The event horizon is defined by the existence of a singularity at the heart of the black hole. If there is no singularity, then the nature of the event horizon could be fundamentally different from what we currently believe. Kerrs' theories suggest that instead of being drawn towards a singularity, matter inside a black hole might behave in ways we don't yet fully understand. This could have profound implications for our understanding of the event horizon and the behavior of black holes. But it's important to remember, this is all theoretical. We've never been able to observe what happens inside the event horizon of a black hole, and our current understanding is based on mathematical models and indirect observations. Kerrs' theories are an exciting new perspective, but they'll need to be tested and validated against observations. Kerrs' theories could potentially change how we perceive the event horizon and the very nature of black holes. So next time you gaze up at the night sky and marvel at the mysteries of the universe, remember that our understanding of these cosmic giants is still evolving, and who knows? Perhaps one day we'll have the tools to peer beyond the event horizon and see what truly lies within a black hole. Behind Kerrs' theories are complex mathematical arguments that challenge our understanding of the universe. To understand these mathematical principles, let's start with one of the cornerstones of Kerrs' argument. He proposes that the complex mathematics of general relativity, which predicts the formation of singularities, is not a perfect representation of physical reality. Think about it this way. If you were to compress a finite amount of mass into an infinitesimally small volume, the mathematical equations would tell you that you've created a singularity. But in the real world, there's a limit to how small you can make something. So, Kerr suggests that the mathematics of singularities might be an artifact of our theoretical model, not a real feature of the universe. He further argues that if a black hole is rotating, there are additional boundaries to consider, like the innermost stable circular orbit, or ISCO. This is the smallest orbit in which matter can stably exist around a black hole. Any closer, and it would be sucked in. But ISCO is outside the event horizon, the point of no return, so it's possible for matter to avoid falling into the singularity. The size of a black hole's shadow, as observed by the Event Horizon Telescope, is about 250% larger than the event horizon itself. This observation supports Kerrs' argument that the physical properties of black holes might be more complex than what our current mathematical models suggest. The key takeaway here is that mathematics is a tool we use to understand the universe. Sometimes it points us in the right direction, but other times it might lead us to conclusions that don't match up with physical reality. That's why it's essential for us to keep questioning, keep observing, and keep refining our theories. These mathematical principles could revolutionize our understanding of black holes and the universe itself. So where does this leave us in our exploration of black holes? The theories proposed by Roy Kerr open up an intriguing new horizon in the realm of black hole research. If singularities, the supposed core of black holes, indeed do not exist, we may need to rethink our understanding of these cosmic behemoths. This could lead to a paradigm shift in our approach to studying black holes. Our focus might move from understanding the nature of singularities to deciphering the alternative mechanisms at play inside a black hole. This could involve studying the dynamics of mass and energy within the black hole and how they interact with the space-time fabric. The implications of Kerrs' theories could also extend to our understanding of the universe's fundamental laws. If singularities don't exist, we might need to reassess the principles of general relativity, quantum mechanics, and their convergence at the quantum gravity threshold. But how do we test these bold theories? One potential avenue could be gravitational wave astronomy. As black holes merge or collapse, they generate ripples in the fabric of space-time, much like the ripples created by a stone thrown into a pond. By studying these ripples, we can glean insights into the nature of the black holes that produce them. Another possibility could be the study of black hole shadows, the silhouette of a black hole against the backdrop of the cosmos, as observed by the Event Horizon Telescope. A detailed analysis of these shadows might reveal inconsistencies with our current models, nudging us towards a new understanding. In the end, the beauty of science lies in its adaptability. Our understanding of the universe is not set in stone, but rather a fluid, ever-evolving entity that shifts and grows with each new discovery. Whether or not singularities exist, one thing is certain. The exploration of black holes will continue to challenge and expand our understanding of the universe.